In this session, we consider moment generating functions. And moment generating functions help us to find things like the expectation or the variance of a random variable. So in general, a generating function is a formal power series in one variable, and it's used to encode information that we are interested in. And specifically in probability, the moment generating functions provide a way of getting results for the expectation, variance, and similar quantities without having to work directly with PDFs or CDFs. Okay, so we've already seen an example of a moment. So supposing there's a random variable x, then the expectation of x, we also write mu of x, that's called the first moment of x. Okay. Now, then the expectation of x is called the first moment of x. The expectation of x squared is called the second moment of x. The expectation of x cubed is called the third moment of x. Collectively, these are called moments. And moment generating functions are used to simplify the calculation of moments. Okay, so recall that if you have an exponential function, then it's Taylor series about, so exponential of x or e to the x. Its Taylor series about x equals 0 is the infinite series 1 plus x squared over 2 factorial and so on, or summation n equals 0 to infinity x to the n over n factorial. And this converges for all real numbers x. Now, the moment generating function for x, the random variable x, is defined like this. We write m sub x of t is the exponential of t to the x. Remember, when you're calculating your expectation, either by doing sums or by doing integrals, you're going to go through all the possible values of x, and then this will be a function of t. Okay, so the moment generating function for x and m sub x of t is the exponential, is the expectation of e to the tx. Okay, so you can think of either e to the tx as, so whatever value that x takes, you take the e to that, or you can think of this as an infinite sum depending upon what's convenient for you. We'll do some examples of calculating this moment. Now, does this always exist? If we think of this as an infinite, as the expectation of an infinite series, and the calculations may result in an infinite series, right? The sums of infinite series don't always exist. Okay, so not every random variable will have a moment generating function. Okay, the ones we're interested in this course do, so we can do this. Let's try a very simple example. So we flip a fair coin, set the random variable x to 1 if we get a head. We set x equal to -1 if we get a tail. What is the mgf for x? So let's go through the calculation. So how do we calculate an expectation? Right? So this would be the sum over all x for which are possible for the random variable x. So sum of e to the tx times the probability of that x occurring for a discrete random variable, right? So what are the values that x can take? They can, in this case, the values that x can take are 1 or -1. So the expectation of e to the tx is e to the t times -1 to the probability of getting -1. Well, that's if you get a t, a tail, and the probability of a tail is 1/2. Plus e to the t times x can take the value +1 times the probability of +1. Well, plus x equals +1 implies that you got an h, and the probability of an h is 1/2. So that's 1/2 e to the -t plus e to the t. That is the moment generating function for that random variable x. Okay. Okay, try another one, this time with a continuous random variable. The previous one was a discrete random variable. F sub x of x, and so the PDF for this x is e to the -x for x greater than 0 and 0 otherwise. Find the moment generating function. Well, what do you have to do? You have to take the expectation of the exponent e to the -x, right? So get back here. Go back to the definition, e to the tx. So how do you do that? You take the function e to the tx times the PDF. The PDF is e to the -x, right? When x is in the right range. And then you integrate that from, in this case, from 0 to infinity. So you take the, right? No point integrating where it's the PDF is 0. So where the PDF is not 0, for x greater than 0. So you integrate for x greater than 0 up to infinity. The function is e to the tx times the PDF is e to the -x dx. And if you perform that integration, you will get 1 over 1 minus t. And this is for t less than 1, actually. If t was bigger than 1, then this improper integral would not converge. If t was equal to 1, then this result is nonsensical, right? So this is for t less than 1. Now, so we found these mgfs. In two cases, we found moment generating functions. But what are these good for? Right? I claim that they were good for finding the moment. Okay. Well, all right. So this is why. There's a small discussion on that. The moment generating function was the expectation of the exponential t of tx. That's the expectation of the summation n equals 0 to infinity t to the n x to the n over n factorial. Now, assuming that we can integrate sums or integrals as required, right? Because you've got, this is expectation, you're either doing it using a sum or by using an integral. Assume that you can, in fact, pull this out, the summation outside, and interchange it with this integral or sum. Can't always do that, but for the random variables that we care about, you can do that. Okay, so if you do that, that's a summation n equals 0 to infinity t to the n exponential x to the n factorial. Look at what's this exponential. This is the moment. This is the nth moment exponential of x to the n. So this is the summation n equals 0 to infinity t to the n. Let mu sub n mean the nth moment of the random variable that we're interested in, divided by n factorial. Okay, well, okay, so the moment generating function, its terms include all the possible moments. Okay. How do I get the moment that I want? Well, if I take the kth derivative of the moment generating function, right? So I take the kth derivative of this sum, which has all of the moments in it. And then I set t equal to 0. Then, except for the kth moment, I'm going to get all zeros. So that gives me sub k. So once again, I calculate the moment generating function. Then I set t equal to 0, right? So I take the moment generating function. I take the kth derivative of the moment generating function, and then I set t equal to 0, and then that will give me the kth moment. Okay, so let's do an example. X is the result of rolling a fair die. X takes values from 1 to 6 with probability 1/6 each. Find the moment generating function. Okay, well, that's a summation. That's the expectation of e to the tx. So that's expectation of e to the tx. So it is, what values can e to the tx take? So e to the t times 1, e to the t times 2, e to the t times 3, e to the t times 4, e to the t times 5, e to the t times 6. So e to the t times 1 times the probability of 1 is 1/6, plus e to the t times 2 times the probability of 2, which is 1/6. E to the t times 3 times the probability of 3, x being equal to 3, which is 1/6. E to the t times x is equal to 4 times the probability that x equals 4, which is 1/6, plus e to the t times 5 times the probability that x equals 5, which is 1/6, plus e to the t times x equals 6 times the probability that x equals 6, which is 1/6. And then I might sort of like this over here. 1/6 e to the t plus e to the 2t plus e to the 3t plus e to the 4t plus e to the 5t plus e to the 6t. This is the moment generating function for that random variable x. Now, supposing I want the first and second moments of this, and I want to find the variance. So what do? I take the derivative of this once, I take the derivative of this. I need the first derivative, I need the second derivative, then I need to set t equal to 0 on those. Okay, so the first derivative, I calculate it this way, and then to get the first moment, the expectation of x to the 1, the expectation of x, I take the derivative, the first derivative, and I set t equal to 0. When I set t equal to 0, then this is 1 plus 2 plus 3 plus 4 plus 5 plus 6. So that's 7/2. Okay, now to take the second derivative, well, I have the first derivative, so then I take the next derivative, and I'll get this thing. And now I set t equal to 0. I will get 1/6 e to the 0 plus 2 squared e to the 0 plus 3 squared e to the 0 plus 4 squared e to the 0 plus 5 squared e to the 0 plus 6 squared e to the 0. E to the 0 is 1. So I will get 91/6. Okay, so now how do I have the expectation already. That's mu1 is 7/2. And now I have the second moment, that's 91/6. What's the variance? The variance is, in moment language, it's mu2, mu sub 2 minus mu sub 1 squared. And that's 35/12. Okay. Okay. Now, as an exercise, think about what happens when you've got an n-sided fair die, equal probability 1/n. What would the variance be? You can show that it's equal to sigma squared is equal to n squared minus 1/12. Okay, the binomial random variable. So probability of a success is P, probability of failure is Q. We're going to do n, small n independent trials. X is the number of successes that happen. So what did we already discussed this? The probability that x equals k equals f sub x of k is equal to n choose k, p to the k, q to the n minus k. Q is the probability of failure, 1 minus p. Okay. So you can calculate the moment generating function for that. And it will be, well, you can work it out. It'll be p e to the t plus q, all to the power n. And you can confirm from this that the first derivative is np. How do you get that? You take the first derivative and you set t equal to 0. The second moment, you take the second derivative and you set t equal to 0, and you should get n times n minus 1 p squared plus np. Now, how do you find the variance? It's mu sub 2 minus mu sub 1 squared. And you should get np times 1 minus p. Okay, another example, the mgf for the geometric random variable. Okay, suppose that the probability of a success in a trial is p and the probability of failure is q is equal to 1 minus p. These probabilities are constant, the trials are independent. Okay. Okay, so we continue doing trials until the first success. Let x be the number of trials, so x can take values 1, 2, 3, and so on. We're just going to keep doing until we get a success. Okay. And, well, we already did the geometric random variable, but you can, if you have to, you can find its PMF by just reasoning it out. And then, once you've done that, you should show that the mgf for that is p e to the t divided by 1 minus q e to the t. Okay, so if I set, if I take the derivative and then I set t equal to 0, I should get mu1 is equal to 1 over p. If I take the second derivative of this and then I set t equal to 0, I should get the second moment mu2 is equal to 1 plus q over p squared. And then the variance is mu2 minus mu1 squared, and that would be q over p squared. Okay. What about the Poisson random variable? So the Poisson random variable, so your x takes values 0, 1, 2, 3, n plus 1, and so on. F sub x of n, the PMF is equal to the probability that x equals n equals e to the negative lambda, lambda to the n over n factorial. We've discussed the Poisson random variable before. And so what's the moment generating function? It's the expectation of e to the tx. So e to the t, that's the summation, e to the t, so this e to the tx is what? So that's e to the t times 0 times the probability of 0 plus e to the t times 1 times the probability that x equals 1 plus e to the t times 2 times the probability that x is equal to 2, and so on. That's the summation n equals 0 to infinity e to the t times n f sub x to the n. Okay. Now, what's this f sub x? This is the PMF for the Poisson random variable. It's e to the negative lambda, lambda to the n over n factorial. So this is summation n equals 0 to infinity e to the t times n e to the negative lambda, lambda to the n over n factorial. Note here that e to the negative lambda is a constant, so we can pull it outside. So this is the summation n equals 0 to infinity, e to the t times lambda to the n over n factorial. But what's this summation? This summation is an exponential. It's the exponential of e to the t lambda. So that's e to the negative lambda exponential e to the t times lambda. So that's the exponential of lambda e to the t minus 1. That's the mgf for the Poisson random variable with parameter lambda. So if you take its first derivative and then set t equal to 1, you should get lambda. And if you take the second derivative of this and you set t equal to 0, you should get lambda squared plus lambda. What's the variance? It's equal to mu2 minus mu1 squared, which is lambda. And this might be easier than the other way that we did it from the definition. Okay, so some properties of MGFs. If you have a if you have a random variable x and you already know its moment generating function, and then you come up with a new random variable y equals x plus a, then its moment generating function is equal to m sub y of t. That's equal to e to the t a times m sub x of t. Okay, for y equals bx, if you already know the m sub x for x and y is equal to bx, then m sub y of t is equal to m sub x of tb. Okay. All right, so now another case which is useful for us, we've already, supposing x is a random variable with expectation mu and standard deviation sigma, then we can define a new random variable x hat is equal to x minus mu divided by sigma. So that will have expectation 0 and standard deviation 1. Okay, that's can be useful. Now, how is its how are the MGFs of x hat and x related? Well, if you use what we considered before, then the MGF for x hat is equal to e to the minus mu t over sigma times the MGF for x evaluated at t over sigma. Okay, so sometimes if you have random variables for which you already know the MGF and you have some fairly standard transformations of those random variables, then you can find the MGFs for those new random variables sometimes fairly simply. If you know the MGFs for the original random variables. Okay, what about sums of two independent random variables? So let's say you have x and you have y, and you know their MGFs, and they're discrete independent random variables with PMFs f sub x, f sub y, and joint f sub x, y. As x and y are independent, f sub x, y equals f sub x times f sub y. So let z equal x plus y. Okay, independence is important here. So don't apply this result everywhere, only where we have independence. then it's the mgf for z is e to the tz, the exponential of e to the tx plus ty. So that's e to the tx times e to the ty. Then you do the double sum of e to the tx times e to the ty times the PMF to get the expectation. Okay. And because these are independent, you can pull out the things with x in them as you're summing over y, for example. And you'll get that the the mgf for the sum of the two independent random variables is the product of the mgf for the individual random variables. Remember, these have to be independent random variables, statistically independent random variables. Now, the same result holds for continuous independent random variables, and the proof basically involves replacing the summations with integrals. Okay. Now, the uniqueness of MGFs. Can two MGFs have, can two different random variables have the same, which have the same MGF? How similar are they? Okay, so suppose that x and y are random variables. They have MGFs m sub x and m sub y. And in fact, m sub x of t is equal to m sub y of t for all values of t. Then x and y have the same PDF, so they're essentially the same random variable. Okay, so proof is not, it's beyond this course, but it's a result we can use. Okay, suppose that we are given the MGF m sub x for a single random variable, and m sub x of t is equal to 1/3 e to the t plus 2/3 to the fifth. What's the PMF for x? So now, for the recall that for the geometric random variable, m sub x of t was p e to the t plus q to the n. So here, if p is 1/3, and then q is 1/3, and then n is 5. So that means that, and then by the uniqueness theorem, x is the geometric random variable with p equals 1/3 and q equals 2/3. So then once you know that it's the x must be the geometric random variable with these parameters, then you just look up the PMF for x. Okay. Supposing that a random variable x is an MGF given by m sub x of t equals e to the 3 e to the t minus 1. What is the PMF for x? Okay, so what you do is you say, what do the PMFs of various random, what do the MGFs of various random variables look like? And you say, well, for the Poisson random variable, we said it was exponential lambda e to the t minus 1. So exponential of lambda e to the t minus 1. Okay, so this is the this MGF is the MGF for a Poisson random variable with parameter lambda is equal to 3. So once you know that, then you say, well, what's the PMF for a Poisson random variable? Okay. Suppose x is a binomial random variable, with parameters m and p. So m trials, probability of p is the success probability, remember? And y is a binomial random variable with parameters n and p, and they're independent. We define a new mgf for z, that's equal to x plus y. Find the PMF for z. Okay, so for the binomial random variable, we found that m sub x of t is p e to the t q to the m number of trials. And y, for y, it's p e to the t plus q to the n. Okay, and these are independent. So the MGF for their sum is the product of the MGFs. Okay. All right. So that ends our introduction to PMFs.